Hey guys, today we have a short lesson that's just looking at some of the different factors that affect or limit how large a population can become in a given ecosystem. So in this lesson on limits on populations, we're going to be looking at something called biotic potential, and you do have to know the different factors that regulate a species' biotic potential. Then we're going to look at the difference between density-dependent limiting factors and density-independent limiting factors, and you do need to know examples of both of those. Then we're going to look at something called carrying capacity and how it affects dynamic equilibrium. And then lastly, we're going to look at how we can describe species as specialists or generalists, as well as something called the law of minimum and the law of tolerance. So biotic potential is just the maximum number of offspring that an entire species could produce if resources were unlimited. So if they weren't competing for food or shelter or water or anything like that. The higher the biotic potential, the faster the population can grow, because obviously the more offspring you have, that's contributing to the population size. There are 4 different factors that control the species' biotic potential. One is birth potential, which is just the number of offspring that a single individual can give birth to at once. So like for humans, our average biotic potential is just 1. Definitely you can have multiples like twins and triplets and stuff like that, but most people just have 1 at a time. Whereas like the birth potential in dogs might be like 8 or something. I'm just making that up, but whatever the average litter size would be. The second factor is the capacity for survival. So that is just the number of offspring that survive to reach reproductive maturity, or essentially like how many of them survive until puberty. And usually this is like inversely proportional to the birth potential. Species that have a fairly low birth potential tend to have a fairly high capacity for survival, whereas species that have a really high birth potential that might give birth to hundreds of offspring tend to have a low capacity for survival. They might only have like 5% of those hundreds of offspring actually survive to maturity. The third is breeding frequency, which is just the number of times a species can reproduce in a year. So if a species has like a specific mating season and they only mate during that time of the year, that would reduce the breeding frequency. So would just a really long gestational period. So if you get pregnant and then are pregnant for most of a year or more than a year, that would also reduce the breeding frequency, as opposed to species that can get pregnant at any time of the year and have fairly short pregnancies. They would have a higher breeding frequency. And then the fourth is the length of reproductive life, which is just the number of years that an individual can reproduce for. So if a species matures very quickly and then can breed for their entire life, that would be a long reproductive life. If a species like humans takes a long time to reach reproductive maturity, and then like female humans at least are not able to reproduce for their entire life, women hit menopause and then can't reproduce anymore, that is a much shorter reproductive life. So all of those kind of come together to determine the overall biotic potential of the species. Okay, limiting factors, which are factors that limit the size or the growth rate of a population, can be both biotic or abiotic. And all of these factors are essentially different ways to limit a species or a population from reaching its biotic potential. So it's essentially kind of limiting that species' ability to hit its maximum number of offspring, and therefore limiting its growth rate. Abiotic limiting factors include things like not enough sunlight, not enough water or oxygen if we're talking about an aquatic ecosystem, not enough nutrients, or it could be things like the temperature is too high or too low, or there's like pollutants in the area, stuff like that. Biotic limiting factors include things like lack of food, if there's a lot of predators in the area, if there's diseases or parasites, or if your species is just being outcompeted by a different species. These factors will differ from ecosystem to ecosystem and can even fluctuate from year to year or from season to season within an ecosystem. And these limiting factors can be either density dependent or density independent. If we're talking about a density independent factor, what that means is that this factor will affect all populations in the area the same, regardless of the density of that population. So how closely together or how crammed together the individuals of that population are doesn't matter. So this includes things like natural disasters, man-made disturbances like habitat destruction, pollution, contamination, and climate change. Essentially with these factors, it's like, you know, if you're in that ecosystem and a volcano erupts, you're going to be impacted whether you have a population of 100 or a population of 10. Size and the density of your population doesn't matter. If you're in that area, you're all going to be impacted equally. On the other hand, density dependent limiting factors are factors that depend on the density. Essentially, high density populations, so populations that are really crowded, are going to be affected by these factors more than a low density population. These things include food supply. So if your food supply is more limited, it means that there's more competition. And if your population is more crowded, there's going to be more competition. And that includes competition for not only food, but mates, shelter, water, access to sunlight if we're talking about plants. So essentially, the more crowded your population is, the more competition there is for access to the limited resources. If your population is really low density, even if there is limited resources, there's probably still enough to go around. And so your population isn't going to be as affected because you're not as high density. Predation also affects higher density populations more, and that's just because the higher density your population is as a prey species, the more predators your population can support. So there will be more predation in a higher density population. And then also diseases and parasites, they just spread more easily in high density populations. In order to spread a disease or a parasite, two individuals of the species have to come into contact with each other. An infected one can pass it on to a non-infected one. And if the individuals are just super spread out because it's a low density population, then an infected individual might never come into contact with another individual that they can infect. So diseases and parasites spread much less quickly when individuals are spread out. This is why during the COVID-19 pandemic, we're all told to like stay 6 feet apart and socially distance and self-isolate and all that kind of stuff. Why schools were shut down, because schools are a very high density environment, was because diseases spread much more easily the closer together people are. Okay, so we talked about the fact that competition is a density-dependent limiting factor, and there's actually two different types of competition that you need to be familiar with. There is interspecific competition and intraspecific competition. Interspecific competition occurs between individuals of different species. And again, we talked about this before when we were talking about niches, but anytime you have any overlap between the niches of two different species, you're going to have some competition. The more overlap, the more competition there will be. So if you have a slightly shared or overlapping niche, you're going to have interspecific competition. This is also the type of competition that you get between a native species and an invasive species. Again, we talked about sometimes they can have completely overlapping niches. Intraspecific competition is competition between individuals of the same species. So in the example here, two frogs competing for the same resource of food, in this case, the fly. And it could also be competition for mates, would be an example of intraspecific competition. And yeah, intraspecific competition goes way up the more crowded it is, because again, you're competing with individuals of your own population for access to resources. Okay, carrying capacity is the maximum number of individuals of a species that an ecosystem can support. So you're only looking at one species or one population at a time when we're dealing with carrying capacity, and it's just saying how many people or how many deer or whatever can this ecosystem support. It is based on the availability of resources, so it can fluctuate based on the year or the season or whatever. If you've had like a drought and there's not enough food to go around, that's going to bring down the carrying capacity. That ecosystem can support fewer individuals. Populations that are below carrying capacity will always continue to grow until they reach carrying capacity. Populations can go above carrying capacity temporarily, but once populations go above carrying capacity, the death rate of that population will increase until they are back down below carrying capacity. Populations will fluctuate in size because the limiting factors will change from time to time. However, the community as a whole, when we take all of the different populations into account, tends to remain stable. And that's because each individual population is able to make these changes and adaptations in order to maintain the entire community. When, say, for example, a prey population starts dropping down, the predator population will drop down to match that. And when the prey population goes up, the predator population would go up. That is called a predator-prey cycle. So changes in one population will influence changes in other populations. They're all kind of reacting together in order to maintain the overall stability of the community. As long as no population stays above carrying capacity, which will not happen naturally, the ecosystem will stay in equilibrium. So this is just kind of an example of what this could look like, this kind of carrying capacity situation. So in this case, the red line is our deer population, the blue line is the carrying capacity or the maximum number that can be supported by that. So the first thing I want to point out is the fact that carrying capacity can change. In this case, the carrying capacity has dropped, probably because resources are more limited for some reason. And then obviously this red line, we see it increase, and it will increase always. Any population will increase until it hits the carrying capacity. In this case, it has gone above carrying capacity, and that's fairly common for a population that's growing like this one. And that's because children, or baby, whatever we're talking about, deer in this case, don't require as much resources as full-grown deer or adults or whatever. So this population might be growing and growing and growing, and all of a sudden it has like 50 adults and 30 kids, and it can support that until those kids grow up and now you have 80 adults and there's not enough food to go around for 80 adults. And so at that point, you have this kind of die-off that we see right here, where however many of them starve to death, and then we get back down below carrying capacity again. And you oftentimes see what's called an undershoot, which is going way down below carrying capacity, not just going to carrying capacity and then leveling off. And that's because instead of, like, okay, so say you had, just for simplicity's sake, enough food for 10 individuals, and there are 12 individuals, so 2 need to die. It's likely that those 2 that need to die still get some of the food. They don't get enough to survive, but they don't just not eat any of the food. And so because they have taken some of the food, despite the fact that they're going to die, now there's not enough food for 10 individuals, because some of it has been taken by the 2 that are going to die. Now there might only be enough for like 8 individuals, and so you have 2 more that are going to die. So because the ones that there's not enough food for still take some of the food, it means that you end up actually having like more die than what would need to if you just like completely cut off the food supply to some of them right off the bat. So we have this undershoot of the population. Eventually, it does kind of stabilize out at the carrying capacity, but there's probably going to be like a couple overshoots and undershoots that get smaller and smaller until you stabilize out. Okay, tolerance is the species' ability to survive under certain circumstances, which might not always be ideal. So the law of minimum states that the nutrient that is in lowest supply will be the one that limits growth. So it's essentially saying, like, if a plant needs equal amounts of nitrogen and phosphorus to grow, but there is less nitrogen available, it'll be the nitrogen that determines how much the plants grow. So whichever one the plant's community has less of, that's the one that will limit growth. The law of tolerance states that an organism can survive within a certain range of abiotic conditions. If they go outside of those conditions, they will die. So for example, that might be like temperature. Like we all have a temperature that feels like ideal to us, which is like, you know, it varies from person to person, but say like 78 degrees Fahrenheit, like, or whatever room temperature is. But obviously you can survive outside of that range. You can survive if it's like 63 degrees Fahrenheit, or you can survive if it's like 88 degrees Fahrenheit. Like, and I'm using degrees Fahrenheit because that's how the thermostat in my house is. But obviously you're not going to be comfortable. You might be too cold and be shivering, or you might be too warm and be sweating, but you can survive within that range. But if you get outside of that range, if you become too cold, you can become hypothermic and die. If you become too warm, you can become hyperthermic, or essentially have a heat stroke and die. So there is a range that you can survive in. There's like kind of your ideal whatever condition, in this case temperature, but it could be talking about like pH or nutrient availability or amount of water or whatever. So there's the ideal amount, and then outside of that you have a range that as you move further away from the ideal just gets more and more uncomfortable, but is still survivable, and then eventually you get outside the range of survivable into what is going to kill you if it's maintained. The larger that range of tolerances though, the better able that species is at surviving fluctuating conditions. And the closer that species is to its ideal level of whatever we're talking about, the closer that species will be to its biotic potential. Okay, last few definitions, kind of in terms of that range of tolerance. We have a specialist, which is a type of species that has a really narrow tolerance range for some or all conditions. Some specialist species are also called indicator species because their range of tolerance is so narrow that as soon as there is like the slightest change to their environment, they start dying off. They're like the first species to start dying when there is a change. And so they're kind of the first indicator for us as humans that are monitoring these ecosystems that something is happening that could start impacting other species. They're kind of like, if you've ever heard of the example of the canary in the coal mine, that's like, you know, when back before technology would allow us to detect gases in the air, back when like miners were working underground, they would bring a canary, which is kind of bird, down with it. And the canary was more sensitive to poisonous gases in the air. And so if the canary keeled over and died, that would be your sign as the humans in there that you should evacuate the mine before people started keeling over. And so that's kind of what the indicator species is for us in an ecosystem. It's the first one to kind of start keeling over, and it's the sign that if we don't do something to help this ecosystem, whether it be get rid of pollutants or whatever, we need to stabilize this ecosystem or there's going to be more species starting to die off. A generalist species is one that tolerates a really wide range of conditions, which does mean that it's a lot better able to survive things like pollution and natural disasters and climate change and all that kind of stuff. It also makes for really good invasive species. Most invasive species are generalists, which allows them to be taken out of their native habitat, plopped in a new habitat with completely different environmental conditions and food that they've never seen before, and they still thrive even better than a lot of native species in that area. So yeah, generalists make really good invasive species. Okay, that's it for today's lesson. I hope you learned something new.